we have one of the desktop process units built by students to demonstrate PID control on a motor speed system. We have a DC motor driving a DC generator. As the motor spins, it drives the generator, spins it. The generator makes a DC voltage signal, which is read by the controller. The controller then uses the PID algorithm to determine how much power to send to the motor to keep the motor at a constant speed. What we have connected here, which is slightly different from previous videos, is a computer connected to a data acquisition unit, so we can actually graph the motor speed and graph the controller's output. So let me demonstrate here. I'll put the controller in manual mode. I'm going to spin this up to about 40% output. We can display the speed of the motor, about 35%. You can see over here on the computer screen, our controller output stepped up as I twisted the knob by hand, and the motor speed has come up correspondingly. If I now take my finger and slow the motor speed down, we're going to see a drop in motor speed with no change at all in the controller output. There's my drop in motor speed. No change in output because the controller is in manual mode. The controller is ignoring changes in motor speed, and what it's doing is simply keeping a constant output signal to the motor. What I'm going to do now is place this in automatic mode. So over here I'm going to push the auto manual button, and now we're in automatic mode. Now what's going to happen is if the motor slows down at all, the controller will see that and immediately respond by sending more power to the output. So back to our screen, we can see this as I touch the motor speed. The speed drops a little bit, but then the output rises. It is fighting that change. If I let go, it oscillates a bit and then stabilizes. It tells me this controller has a little too much gain. But you can see here, it's more difficult for me to slow the motor down. I can't get a drop down like I could before very easily because the control system's actually fighting that change. If I go back to manual, I can demonstrate one more time what it's like in manual mode. I can slow the motor down very easily because the controller's not fighting that change. Now I'm going to make some tuning changes. I'm going to throw this back in automatic mode. I'm going to hit the tune button. My gain of 1 is too high, and I can tell that by the way it oscillated after I gave it that load change. So I'm going to go to a gain of about 0.33. And then going back to the screen, if I slow the motor down, I see the output rise. It's a little easier to slow it down because it's not as aggressive control actions we had before. However, when I let go of it, we don't see the oscillations we did before because it's not overreacting. So I've killed my oscillations, which is a good thing, but the expense, the price I pay for that, is having a controller that doesn't correct quite as aggressively as I'd like it to when it sees a change in load. So here's what I have to do. I have to add another control action to my controller, not just proportional control, but now integral. So I'm going to hit the tune button, and I'm going to reduce my integral time to a much, much shorter time constant. This is going to have the controller respond to error over time by ramping the output either up or down. So I'm going to go with a very aggressive integral time, which is necessary for this fast-acting, self-regulating process. Now, focusing back on the screen, as I slow down my motor, it aggressively ramps up the power to the motor and does all it can to hold it at speed. I almost can't get this thing to slow down more than 1 square on the screen. If I let go, it overshoots because of all the output that got built up during the integral wind-up period. When I let go of the motor shaft, it briefly oversped, then corrected itself. Once again, I'll slow the motor shaft down with my finger. We see the motor speed drop a bit, but very quickly correct, aggressively correct, because of that integral action. When I let go, I get a bit of an overshoot, but there's no persistent oscillation like we have in proportional control. This is much better control behavior than what we had before. And it's easy to see with the graph, process variable changes and output changes relate to each other. In manual mode, like this, and in automatic mode, like this. Got ourselves a working control system. We can examine the dynamics on the screen of a computer.